This is Angela Galloway, and I will be talking to you today about Math 146, Unit 3, which covers Chapter 8. There is one section of notes, or there's one file of notes on our Blackboard page for Chapter 8, so all the sections are included in there. I think on this video I'll probably just go through 8.1, 8.2, and 8.3, and then I'll save the other ones for another video just so this video isn't super long. So what we're going to be talking about in Chapter 8 is graphs and functions. So this, unlike some of the other chapters that we've done, should be a little more like some things you've covered before in math classes. So you've probably seen these types of equations and processes before somewhere, unlike some of the voting methods and maybe some of the financial stuff we talked about in our other units. So hopefully you'll have some recollection of some of these ideas, so it won't all be totally new topics to you, but if it is a new topic, you still should be okay. We're going to go through everything and try to explain it all. So what we're doing here in Chapter 8, this would be 8.1, which is just kind of the basics of graphing, okay? So when we're talking about graphing, we're looking at the XY plane, okay? So the x-axis is the horizontal axis here. The y-axis is the vertical axis. So all our x values will be plotted from these numbers here. All our y values will be plotted from these values. Now this is called the origin here at the center there, and that is where x is 0 and y is 0. Okay, so that's also called the origin. Now, how do we write out these points that we're going to be talking about? This is our ordered pair. We write the x value first and then the y value. So they're in parentheses, and that tells us it's an ordered pair. You have the x value, then comma, the y value. And then we use that x and y value to tell us where the point is. The x value tells us if we go left or right. The y value tells us if we go up or down. Now the way we know if we go left, right, or up, down is if it's a negative or a positive. A negative value of x is over here. So this line technically goes out to negative infinity there and would go out to positive infinity over here, you know. For the y's, when you go up, you're going towards a positive infinity. When you go down, you're going towards a negative infinity. Okay, so for x's, the right is positive, the left is negative. For y's, up is positive and down is negative. Okay, so over here, just plotting some points. Let me erase some of this real quick to make it a little easier for us to read. Okay, so here we plotted just a few different points. So let's look at point A here. Point A says it has a point of 3, 1. Okay, so the x is 3, so that means we're going on the horizontal axis. We're going 3 to the left, so 1, 2, 3, right? Here we are at 3. Then it says the y value is a positive 1, so that means we go up 1, right? And so that's how we end up right there at that point. So that's at 3, 1. A negative over here, if we look at C, it's got a negative 5 and a positive 6. So negative 5 is our x value. So we go over here to negative 5. So we're going to the left now. 1, 2, 3, 4, 5. Here's my negative 5. And then a positive 6. So I go up 6 spots to this, and that's how I get to that point. Okay, so when we plot a point, we're using both coordinates. We're using the left and right, which comes from our x coordinate, and the up and down, which comes from our y coordinate. If one of the values is a 0, then that means it's going to be on one of these axis lines. So it's either going to be sitting on the x-axis or the y-axis. Okay, so like this one here at negative 5, 0, we go over the negative 5, but because the y is 0, we don't go up or down any. We just stay right on the line. So these are actually separated into 4 quadrants. So you'll notice, each of these lines here kind of give us a little quadrant. So this is called quadrant 1. This is quadrant 2, 3, and 4. So this actually goes in a counterclockwise direction, the way we define our quadrants here. In the first quadrant, everything is positive. So X is positive, and Y is positive. Okay, so if you have two positive numbers, they're going to be plotted over here. Okay, over here in quadrant 2, X is negative, right? Because over here we're on the left side of X, so we're negative X's, but my Y is still positive because I'm still on the upper half of the Y's. Now when I go down here, what values am I going to have? Well, I have a negative X, right? And then since we're going on the bottom side here, we're actually a negative y, right? So negative x and a negative y. Over here, I'm back to the right side of the x's, so I have positive x's, but I have negative y's still, okay? So that's just something to note that, if you are in a certain quadrant, it's going to have a certain positive or negative values of x and y, okay? All right, so some of the equations that we're going to be using here, one is talking about standard form. So this is one way to write out the equation of a line. When you are asked to do it or give your answer in standard form, what they're talking about is that your x values and your y values are on one side of the equation. On the other side is just your constant or your number, okay? So that is standard form. You'll want to know that because you will have some homework problems that ask for the answer in standard form, so you want to know what they're asking for. Then we want to look at how to find the x and the y intercept. Now the x and the y intercept, what we're talking about there is when it crosses either the x-axis, that would be the x-intercept, or when it crosses the y-axis, that would be the y-intercept. Okay, so like for example, this point here would be an x-intercept because it's crossing it's a line on, or a dot in this case, on the x-axis. Okay, so we're looking for where does it cross the x and the y axis. So to find the x-intercept is defined like this. It's going to be some x value, but the y is going to be 0, right? Because it's going to be sitting right on the x-axis. So to find this x-intercept, when we have the equation, we can just plug in 0 for y, and then solve for what x is. And that should give us what the x-intercept is. To find the y-intercept, we just do the opposite. We plug in 0 for x and solve for y. Okay, and we'll do some examples of those, of course, as we get to that. We also can find the slope of a line. The slope of the line is telling us how quickly our line is rising or falling. So the bigger the slope, the more steep the line is, because it's saying it's rising very quickly. Okay, so slope can be positive or negative. We see here that a positive slope, we're always looking or reading the graph from left to right, just like we would read a sentence. Okay, so we're looking from left to right. Is the line rising or is it falling? Okay, if it's rising from left to right, then it's a positive slope. Okay, so our slope should have a positive value. If we're looking at it from left to right and it's falling, like this one, then we have a negative slope. Okay, so our slope should be negative. Then there's two other special cases where it's not negative or positive. One is if we just have a flat line, which would be a horizontal line, then we say the slope is 0, because at that point it's not rising at all, right? It's just totally flat. So we have a slope of 0, and that would actually, the equation of that line would look like y equal to some number. Okay, so like this case might be y equal to 3 or something like that. So it'll be y just equal to a number. If we have a line like this, so it's a vertical line, then that looks like this, x equal to a number. So let's say this is maybe x equal to -3 since it's over here on the left side. If we have a line like that, it's actually called an undefined slope because what I usually try to think of is this is undefined because, when we're calculating slope, we're trying to find how quickly a line is rising, right? And this one is rising just constantly. It's rising so quickly that we can't even define it or calculate it. So we just call this the undefined slope, okay? Now, if we're trying to calculate the slope of a line, what we need is 2 points. Okay, so like here we've got a point here and a point here that both fall on the line. Then to find the slope, using those 2 points, what we do is we take the y's and subtract them, and then we take the x's and subtract them. This is also sometimes called the rise over the run. So we're looking at how quickly the line is rising over how quickly it's running, going, from left to right. This is up and down, left and right. It also can be called the change in y over the change in x. This little delta symbol there means change in math language, I guess. Sometimes it's written that way, talking about the change in y over the change in x. And like I said, we're going to do lots of examples for these, okay? All right, find the x and the y intercepts of 2x minus 5y equals 10. Okay, so this would be considered in standard form right now because it's got the x's and the y's together and it has the number over here on the right. So if we want to find the x-intercept, we're going to let y equal to 0. So that's what we're always going to do when we find the x-intercept. We're going to let y equal 0. So I'm going back to this equation here. I'm plugging in 0 for the y. That's what I did here. So then I get 2x minus 0 equals a negative 10. I'm going to divide everything by 2 to get x by itself, and then I get x equals a negative 5. So my x-intercept is this negative 5, 0. Okay, that's my x-intercept. Now to do the y-intercept, I let x equal to 0, so I go back to this original equation, plug in a 0 for x, and I solve this. So now I get negative 5y equals negative 10. I divide both sides by negative 5, and I get a 2. So now my y-intercept here is 0, 2. Okay, so that's how we could find x and y intercepts. Now find the slope of the line that passes through the points 4, 4, and 6, 8. So if I have 2 points, I can find the slope, right? The slope here this is the slope formula. M equals, so M is what we use to represent slope. M equals y2 minus y1 over x2 minus x1. So looking at these, it doesn't matter which one you label as like Y1 or Y2, okay, as long as you're consistent with which Y goes with which X, okay? So when you're looking at these, you want the Y to be right on top of the X that it goes with, okay? So like here in the point, it's 6 and 8, and then you see 6 and 8 are together here, then we've got 4 and 4, and they're together, okay? So it wouldn't matter if I did 4 minus 8 over 4 minus 6, or if I do 8 minus 4 over 6 minus 4, I'll get the same answer. But you just will always want to make sure you have your points lined up together like this, okay? So we plug this in, I get 8 minus 4 divided by 6 minus 4, that gives me 4 over 2, which gives me 2. Okay, so my slope is 2. So what does that mean to me? Well, since it's a positive value, that means that if I saw an equation of the line, it should look like an increasing line, right? So because it's a positive slope, that means I have an increasing looking line. So my line is going to be rising from left to right. Okay, this says find the slope of the line that passed through the points 2, negative 3, and 2, 7. Now you'll notice in this one that x is actually the same in both of these. So let's see how that plays out when we plug this in. The y values, here we get 7 minus a negative 3, and then 2 minus 2. So I get 10 over 0. Well, then I have an issue, right? Because if you put this in your calculator, you're going to get an error message because it's going to say you can't divide by 0. And that's true. We can't divide by 0. That gives us an undefined answer. So 10 divided by 0 is undefined. An undefined slope means that our graph looks like this, right? It's a vertical line. It's one of those special examples that I talked about just a second ago right here. This is the undefined slope when it's up and down. So we know it looks like this, so we could go back and say, well, what value is this? It would be x equal to 2 because you see both of our x values here are 2. So that means every x value on this line is going to be 2, and that's going to be our equation of the line. It's just going to be x equal 2. I didn't ask us for that on this one, but I'm just kind of working ahead to tell you how you would find the equation of that line. Okay, so thinking about slope as a rate of change. So slope, in real life examples, we think more of it maybe as a rate of change. So how quickly is something changing over time. So here in the Mojave Desert in California, temperatures can drop quickly from day to night. Suppose the temperature drops from 100 degrees at 2 p.m. to 68 degrees at 5 a.m. Find the average rate of change and use it to determine the temperature at 10 p.m. Okay, so this one is a good example, although it can get a little confusing about the time that we've got there. So when we're setting up our x and y values here, we need to determine, what's our x and what's our y. Um, so for this one, we've got time as x and temperature as y. Okay, and the way I've got that, since they didn't really tell us that we're probably going to want to do the change in temperature over the change in time. That makes a little more sense. But we can also see here that they already had set this up, and so we know the y's are on top, so that's going to be our y value there. But so our time, we've got 2 p.m., it's 100 degrees then, and at 5 a.m. it's 68 degrees. Okay, so we're going to plug this into our formula. So 68 minus 100 and 5 a.m. minus 2 p.m. Okay, that gives us negative 32 degrees divided by 15 hours. So the 15 hours is what's a little confusing sometimes. You see the 5 and the 2 and you think, well, shouldn't that be 3 hours? It's like, no, and then, it just gets a little confusing. So how did they get 15 hours? They went from 2 p.m. to 5 a.m. the next day. So you can think of like 2 p.m. to midnight is 10 hours, then midnight to 5 a.m. is 5 more hours. So that would give us our 15 hours. So that's where they got that from. So anyway, so what we get to here is negative 2 degrees Fahrenheit per hour. So that's our rate of change. The temperature is decreasing because it's a negative 2 degrees Fahrenheit per hour after 2 p.m. So that's what we could use it for there as a rate of change. Here we can also think of it as how something is changing. A certain boutique chain of stores was comparing the square footage of their stores to the sales of their stores. Two stores had the following values. So we're looking at how square footage of the store and revenue of the store relates. Okay, so in store one, we had 1.4 thousand square feet, which would be the same as 1,400 square feet, right? It's just the way um, they're talking about their units. So in this one, square footage was in thousands of square feet, okay? And then 1.1 million in sales. Store 2 had 1.9 thousand square feet and 3.2 million in sales. So this is our X and our Y. We've got 1.4 comma 1.1. So this stands for 1,400 square feet. This stands for $1.1 million. Here we've got 1.9 comma 3.2. So the first thing we want to do here is calculate the slope. So we plug in our Y and our X values here and we get 4.2. If we wanted to explain what the slope means to the owner of the boutique, what would we say? Okay, so once we get this number, we want to be able to interpret what 4.2 means. If I just went back to the owner here of this boutique and said, well, I calculated your slope and it's 4.2, that might not tell them very much, right? So we need to help explain what that number means. So 4.2 is telling me that as we increase square footage, 1,000 square feet, the sales are going to increase 4.2 million. So the way to get to that is let's think about our units that we're using here, right? So we've got our Y's over our X's. So our Y's in this case are $1 million in sales, right? Our X's are thousands of square feet. So that's what I've got down there. So if my answer comes out to 4.2, the unit is $1 million over thousands of square feet. So it's $4.2 million per 1,000 square foot. Okay, so every 1,000 square feet I add on, I shouldn't expect to get sales to increase 4.2 million. If the owner had an opportunity to increase one of her store square footage by 200 square feet, how much would we predict that her sales would increase? Okay, what can be a little tricky on this one and several real world problem examples is we always have to be careful of what units we're using, okay? So like here it says we're increasing it by 200 square feet. So it might be easy to just say, well, I just need to plug in 200, right? Because I'm increasing it 200 square feet. But we need to think about in this situation, what does an X of 200 mean? If X was 200, when I plug in 200 here, that's talking about 200,000 square feet, right? So we're not talking about 200,000 square feet. We just want 200 square feet. So we need to figure out what is that in terms of thousands of square feet, right? So I take the 200, divide by 1,000, and I get zero point 0.2. So if I'm talking about 200 square feet, that's the same as 0.2 thousand square feet. Okay, so I'm plugging in the 0.2, and I'm going to multiply it by 4.2 million. Because remember we said for every 1,000 square foot, our sales increase 4.2 million. So if I multiply by the number of 1,000 square feet I have, that's going to tell me how much my sales will increase. And so we can see here we get 0.84. And then once we get the 0.84, we have to be able to interpret that. What does 0.84 mean? 0.84, is that 84 cents? Is it $84? What is it, right? So we go back up here and we say, what is the Y value? The Y value is in millions of dollars. So we would say it's 0.84 million, which we could write out as 840,000. Okay, moving on to 8.3. In 8.3, we look at some new equations and how to figure out the equation of a line. So the most commonly used form that we use for the equation of a line is slope-intercept form. So we already talked about standard form, which was just the ax plus by equals c. But now we're going to talk about slope-intercept form, which we're going to see probably more of and you've probably heard of before. So slope-intercept form is written in this way: y equals mx plus b, where m is our slope and b is our y-intercept. So if we already have the equation written like this in the y equals mx plus b form, then it can be very simple for us to find the slope and the y-intercept without having to do too much else. So if I have this equation, y equals 5x plus 2, I can find the slope. So this one said find the slope by just looking at which value comes before x, right? The x is right before the x, or the 5 is right before the x, so our slope is 5. Now this next one is almost in slope-intercept form, right? Except that we've got a 4 times the y. We want y by itself. So if I rewrite this by dividing everything by 4, now I get y equals 1/2 x plus 3, and now I can see that the slope is going to be this 1/2 here, right? So my slope is 1/2. So if you can get your equation into slope-intercept form, or if it's already in slope-intercept form, then when you're asked to find the slope or the y-intercept, we can do that just by looking at the equation of the line. Another form that we have is point slope form. Point slope form is going to be helpful when we have the slope of a line and we have a point on the line. If we have both of those things, then we can plug those into point slope form and find the equation of the line, okay? So find the equation of the line with slope of -2 that passes through the point 5, 8, and then it says give the answer in slope-intercept form. So it's saying at the end of all this, when we solve everything, we want it to come out so that y is by itself on the left and the x and the constants are on the right, okay? So now we're going to use this equation because we have a slope and we have a point. So that's why we use the point slope form. I'm going to plug in my values. So I'm going to have y minus my y1 is 8, comes from here, equals -2 is my slope times x minus 5. So that's my x value. Okay, so once I've got the equation set up like this, I'm going to distribute my -2 into the parentheses. So I'll have y minus 8 equals -2x plus 10. All right, now I'm just going to solve this equation for y. So I'm going to add 8 over here, add 8 over here, and I get y equals -2x plus 18. And that would be my answer. Okay, that is the equation of the line that has a slope of -2 and goes through the point 5, 8. Okay, so I said we can use the point slope form when we have one point and we have the slope, but we actually can also use it when we're given just 2 points, okay? Because when I have 2 points here, like this, I can find the slope of the line, right? And then once I find the slope, now I have the slope and I have 2 points to use in my point slope form, okay? So first let's find the slope. So the slope of this one, we do y2 minus y1 over x2 minus x1. That gives us a -1/2, okay? So I'm going to plug this into my point slope form down here. Y minus y1 equals m times x minus x1. Now what I did here was I showed my students how it doesn't matter which point you use, either one will give you the same answer. And that seems kind of weird because it's like, how could I plug in 6, 1 or plug in -2, 5 and get the same answer? But that is how it works, okay? So what I'm going to do is take my slope that I calculated here. I'm going to plug it into m in this point slope form. And then I'm going to do the same thing over here, okay? But I'm doing it for both points just so you can see that either one you use will work. However, when you're working out your problem, you just need to choose one point, okay? You don't need to do both of them because they're going to come out to the same answer, okay? When I plug in here -1/2 and then I plug in the 6 and the 1, over here, the -1/2, I plug in the -2 and the 5, okay? And so I work all this out. I get it down to slope-intercept form, and it's y equals -1/2 x plus 4. You see they both came out to that. But this problem happened to ask for it in standard form. So if I want this in standard form instead of slope-intercept form, I want to have the x's and the y's on the left side. So I need to bring this 1/2 x over here. So add 1/2 x to both sides, and I get 1/2 x plus y equals 4. And so that would actually be the answer in standard form. Okay, so graphing a line using slope-intercept form. Graph the line y equals 4x plus 1. Okay, so just from this, looking at the equation of this line, I can tell what the slope is, right? The slope is 4, and so I got that from just looking at the line. And then I also know the y-intercept, right? This says plus 1, so 1 is my y-intercept, 0, 1 is the point where it intercepts the y-axis. So the first thing I would do, let me erase some of this here so we can do it ourselves. Okay, the first thing I'm going to do is I'm going to plot this point. So 0, 1. Let me get a different color so you can kind of see what I'm doing here. Okay, so 0, 1 is right there, right? So it doesn't go left or right any. That's the x value. The y value is 1, so it goes up 1. All right, so how can I use my slope to help me know what the next point is? Well, the slope tells me the change in y over the change in x. So if it's a 4, that means it's 4 over 1, right? I can always write a whole number as over 1. There's kind of that imaginary over 1 if I want to write this as a fraction, right? 4 over 1. So this says as x changes 1, y changes 4, right? So if I go over 1 for x, I'm going to go up 4 for y. 1, 2, 3, 4. Okay, and that would be my next point. So that's how I can use the slope to tell me the next point. The other thing I can do, I have down here, is I could plug in points, right? I could say when x is 0, if I plug in a 0, I get y equal to 1. If I plug in a 1 for x, I get 4 times 1 is 4, plus 1 is 5. And so 1, 5 is the next point, which is the point we already plotted, is at 1, 5. So you can do it either way, whichever way makes the most sense to you. And then what we would do, I probably can't even do this, but we would uh, draw a line here, which is going to be a great looking line. But we would connect those 2 points there, pretend like this is a straight line, and it goes through those 2 points, okay? And so that's what we would do for that. Hopefully your line will look much better than mine. The way you're going to do it on my labs is you're going to find your 2 points because you need 2 points to plot a line. You'll plot one of the points, and then as you're plotting the other point, the line will automatically show up on your MyLabs, and so it will draw that straight line for you. Okay, so linear modeling. Often we can find an equation of a line that will fit a set of real data points. It might not fit exactly, but will provide a good estimate of our data, and we can use this for prediction. Okay, so this graph here shows the daily number of workers absent from the assembly line at a certain corporation and the number of defects coming off the assembly line for 8 days. So they're trying to look at, does the number of workers absent have an effect on the number of defects we get on the line. So the line of best fit, or the linear model, is this blue line. So this blue line best fits the data, okay? And we'll talk more about this in our last unit, talking about a line of best fit and linear regression. But for now, we're just going to say, okay, this line fits this data pretty well, okay? And it happens to go through these 2 points here, 0, 9 and 5, 19. So we're going to use those to find the equation of the line, okay? So 519 and 0, 9, we need to find the slope. So we find the slope and it's 2. And then you'll notice that we already have the y-intercept here, right? That's the y-intercept. That's where it crosses the y-axis. So if we want to write the equation of the line, it's just going to be 2x plus 9, right? We actually could already do that quickly. Or we could plug in one of my points with my slope into this equation and get up to this line equation as well. So either way you can do that. But if you notice that you already know the y-intercept, once you find the slope, you can write it in slope-intercept form fairly easily by just plugging in the slope and then plugging in your y-intercept that you have. Now interpret the slope for this example. Okay, so we've got a 2 over 1, right, for our slope. This is the change in y over the change in x. Our y's are the number of defects, so we're going to have 2 defects for every 1 worker absent, right? Or we could say for every 1 worker absent, we get 2 more defects, right? If you have 4 people absent, how many defects can you expect? Well, we do 4 times 2, so 4 times the slope equals 8. So if 4 people are absent, we'll expect about 8 defects. If we only want to allow 12 defects in a day, what is the most number of workers you can have absent? Okay, so that's kind of the opposite of what we're doing here. Instead of multiplying, we want to divide in this case. So 12 divided by 2, which is the slope, gives us 6. And so that means if I was to have 6 workers absent, I would expect about 12 defects, right? So working backwards, you do the 12 divided by 2 to get to 6. Okay, so using our calculator, to be able to do some of these problems. Let's see. I was going to see which equations I wanted to try to plug in here. Let's do the 4x plus 1 in our calculator. Okay, so let me bring up my calculator here. And so we can do a lot in our calculator with graphing. Of course, that's kind of why it's called a graphing calculator, I guess. What we're going to do to graph any line, you're going to go up here to the y equals. Okay, so this is like we have in slope-intercept form, y equals something, right? So we're going to plot that line that was 4x plus 1. That was one we did in our example a second ago. So if I'm looking for the x value, it's right here. You see those different variables there. Uh, when you click that, it's going to give you the x, okay? So you just type in 4x plus 1, then go over here to graph, and it's going to graph it for you. Now, if you don't see it, okay, when you go to graph, if you don't see a line or if you just see a little bit of it, we need to adjust our zoom, how it's zoomed in or zoomed out. So you could go and zoom it in or zoom it out if you want to. Zooming in is going to get closer to it, of course. Zooming out is going to get farther away. But what I usually suggest is at first going to the Z standard, which is number 6. Z standard means it's the standard zoom, and what that is it goes from -10 to 10 on the X and the Y axis. So for most situations, that's going to give you a pretty good view of the graph, okay? Now, if you've got some really high values of X or Y or whatever, then you may need to adjust your zoom in another way by zooming out or zooming in. But for most cases, doing that zoom standard is going to give you a pretty good view of the graph. Okay, so what else can I do with this one? Well, if I wanted to zoom in, so let's say we wanted to find what the y-intercept was, okay? So I could do that by maybe zooming in and seeing if I could find it on here, you know, getting close enough to kind of see it. Or I can get my calculator to tell me where that intercept is, okay? And so I could go to here, I'm going to go to second, calculate. And the X intercept is actually also called the zero of the function. So for the X intercept, I'd go here to the 0. And you see that it crosses the x-axis down here. So what I need to do is it's asking me to go to the left of the intercept. Okay, so I'm going to go to the left of it here and then go up and go to the right of it. So all I'm doing this for is to give my calculator a suggestion of where the x-intercept is. So if you had like a lot of x-intercepts or you had several lines graphed, it wouldn't know where to go. Okay, so on this, we only have one line, so it's a little easier, of course. But the reason why you have to do this is because you might have a line that had several x-intercepts, and you've got to tell the calculator which one you're wanting to find. Okay, then for the guess, you can just push enter again, and then it's going to give you your answer. So it says the x-intercept is at x equal to -0.25, which would be -1/4, and then of course the y is 0. Okay, to get the y-intercept, we go over here to second graph, which is our table. Our table gives us different x values and the y values that correspond to that. So when x is 0, that's our y-intercept, right? So when x is 0, it says y is 1. So that's how we get the y-intercept if we wanted to find that. And also, like if you had a problem that, you know, so if we've got the equation 4x plus 1 and then it says what is y when x is 10, you know, you could scroll down here and say, okay, when x is 10, y is 41. And so you could get that without plugging it into the equation. Now, I did talk about you can also use this lin-reg to calculate the equation of the line. Um, which you can do if you have 2 points. You can plug it into lin-reg, and I think we're going to do that in the next example. Let me see if we are. Yeah, I think I show you that on this example, so we'll just bring that up in a second. The data below shows the number of credential syncing students enrolled at SkyCTC for 2012 and 2014. How could we, so in 2012, we had 2,920 students. In 2014, we had 3,189 students. Oh, excuse me, I'm sorry. Um, how could we use this information to predict what fall 2016's enrollment might be if the growth rate continues at the same pace? For X, we're going to use the years past 2000, and so that is something you'll see pretty often when you're using years. Instead of using the whole year, they'll say use X as a certain number of years after 1990 or after 2000 or after whatever, okay? And so that makes our X value smaller, uh, which makes it more manageable when we calculate our equation. Okay, so how are we going to do this? The first thing we need to do, we've got 2 points that it told us about, but we need to convert those into XY points, right? So we're going to use X as the years past 2000. Okay, so our X value here, we're talking about 2012. So 2012 is how many years past 2000? It's 12, right? So our X value is going to be 12. So that's where I get this value of 12 here. Then my Y value is going to be the number of students. Okay, so I get 2920. Then for our next point, so these are XY points. This is my X, this is my Y. This one is 2014, so that's 14 years after 2000, and I had 3,189 students. Okay, so we want to predict fall 2016's enrollment. So to be able to do that, what we can do is if I can find the line that fits these 2 points, then I could use that line to extend out to 2016 and predict the number of students I'm expecting then. So if this growth rate continues, where are we going to be in 2016? Okay, so the way we can do that is first, what we want to do is find the equation of the line, right? So how could I do that? Well, I need to find the slope, right? Then use one of the points to plug into this equation and I could get the slope. Um, I could eventually get it to the slope-intercept form, okay? So that's how I would do it by hand. We can also do this using our calculator, using something that we're going to talk more about in Chapter 12, our last unit. But what I want to do is go to Stat, and I'm going to go to edit. So the stat button is where we go to do statistics type stuff. And so this is actually a statistics type problem when we talk about linear regression. I'm going to go to edit, and I always go here to edit anytime I have data that I want to put in my calculator. Okay, so what I'm going to do in list 1, I'm going to type my X values. In list 2, I'm going to type my Y values. Okay, so once I've done that, it's stored those in there. I'm going to go back to Stat and go to Calculate. And now I want to calculate the line that fits those 2 points. Okay, and that's what linear regression is for. Okay, and so linear regression, this is going to give us the equation of the line that goes through these 2 points. Now what I need to tell my calculator is where is my X value? So that mine was in L1, and where is my Y value? And mine was in L2. So I do L1 comma L2, and that tells it that these are X values and these are my Y values. So it knows where to pull the data from. So that the list features are the second of the numbers. Okay, so you see the L1, L2, L3, L4. So it doesn't matter where you put your data in the list, you just have to make sure that you pull the right list when you pull this up here. Okay, and then I push enter, and then I get this information here. Okay, so this tells me my slope. It says y equals ax plus b. So a is my slope, 134.5 x plus the y-intercept is 1306. Okay, so that is what I got from there. You could also do this by hand by calculating the slope, right? Doing the y2 minus y1 over x2 minus x1. Once you find the slope, plugging it into here, using one of your points, and then you can find the equation of the line, and you'll get the same answer. This is just kind of a neat way to use your calculator to help you with that. Okay, so I want to know what the enrollment's going to be in 2016, right? So 2016 is 16 years past 2000. So I'm going to plug a 16 into here, and I get 134.5 times 16 plus 1306. I get enrollment of 3458 is what we would expect in fall 2016. Now, of course, this was a little older example from this data. I'd have to look at, if we met this goal or exceeded it or what we did. But this was based on, the rate that we were increasing on these 2 years. Okay, so if the rate changed, if it started to level off or increase more or decrease or whatever, then of course this wouldn't be a good prediction. So it just depends on if that rate of change stayed the same or not. So this would be our answer though, 3458. Okay, so that's the end of this first part of Chapter 8. So this should cover 8.1, 8.2, and 8.3. So you should be able to do any of those homework for your Unit 3. So we have 8.4 and 8.6 to go. We don't actually cover 8.5 in the book. So if you're following along in the book, we don't cover 8.5, but we do all the other sections, okay? So if you have any questions, please feel free to email me at angela.galloway@kctcs.edu, or of course send me a question through the Ask My Instructor button on the My Labs. All right, hope you have a great day. Thanks.